Muldumer. I'm from University of Nottingham, and I will present a paper that analyzes the converter requirements for a double-fed induction machine as used in a flywheel energy storage system. This is a structure of my presentation, and I'll say a few words about energy storage systems in general and application where using flywheels in particular. So typically an energy storage system is used when there is a mismatch between the instantaneous power that is required by a load and whatever is available from a supply. When you size an energy storage system, you need to look at two aspects. One is the size of the energy store, which looks at how much energy in total you need to supply to an application over a given amount of time. And the second one is looking at how fast you need to move the required energy, which gives you actually the power needed. The most efficient energy storage technologies are recognized to be batteries, supercapacitors, and flywheels. The first two are looking at electrochemical energy storage. The flywheel is in fact a mechanical type of energy storage device. Batteries are widely used, but they have some limitations in terms mostly of how much power they could deliver at a given time, and the fact that the charging power and the discharge power is usually asymmetric. Flywheels store energy in a similar way to supercapacitors, and you have here the equation for energy stored in a supercap, which is dependent with the capacity, but also dependent with square of the voltage, so it makes sense to increase the voltage rating. In a flywheel as well, you have energy storage proportional with the moment of inertia, but also square of the maximum speed. And obviously, for that reason, quite a few applications are looking at carbon composite type of rotors spun with a very high speed and enclosed in a vacuum enclosure. The problem typically is how can you extract this power, and what is the energy or the voltage range for which you could get a convenient voltage range and speed range for which you could get a convenient power extraction. As you could see, in most cases you are running in a so-called constant power application. In case of supercaps, power is equal to voltage multiplied with current. In case of a flywheel, power is equal to torque multiplied with speed. And whenever you want to extract electrical power at low voltage or at low speed, that would involve a very large amount of currents or torque. Okay. Whenever you want to interface the flywheel with an electrical system, electrical power system, you need an electrical machine to convert mechanical power to electrical power, and then a power converter that conditions the power as delivered from the stator of the machine to the electrical system. Okay. Typically, in terms of rating, the electrical machine's torque is typically proportional with the weight, but there is no specific limitation in terms of the speed, and for that reason, most compact implementations are looking at high-speed machines running for a given power level with relatively small amount of torque. But this means that we need to use very high stator frequencies in the range of hundreds, if not thousands of hertz. Okay. Also, typical energy storage system applications are like to see the energy storage system as a black box. And for that reason have available the so-called constant power or the power rating at any state of charge. Obviously, in this particular case, you can notice that at minimum speed, the torque typically will reach a maximum, and in the way you design the power converter and also the electrical machine is that you may want to use a machine that is capable of working in a so-called constant power or flux weakening operating mode. There are several electrical machines available which can convert mechanical power back into electrical, and also depending on the frequency and voltage available on the stator terminals, you can have the so-called full converter rating arrangements which are needed. So a power converter that matches the total power of the system, and then you could have as interfaces a permanent magnet synchronous machine, which is typically known to be of high efficiency, but if we use rare materials, permanent magnets can be quite expensive. Also, because the permanent magnet gives you a constant magnetization flux, it's very high to maintain the voltage constant above the base speed, and for that reason, operation in the so-called flux weakening mode requires very large demagnetizing currents, which add up to the requirements or to the ratings of the converter currents, and also make the operation not so efficient. The other problem with permanent magnets is that when you try to operate your flywheel energy storage system in standby, the permanent magnets are still keeping the nominal magnetization in the machine, which means you end up with magnetizing losses quite high, and for that reason you get a relatively fast self-discharge. You could use a different type of synchronous machine, which is the synchronous reluctance, which is easy to produce, doesn't have any permanent magnets or windings in the rotor. The typical DQ saliency also, that's the way you produce electromagnetic torque with this machine, and this is quite ideal for flux weakening applications. A similar situation is with a squirrel cage induction machine. It's also cheap to produce, and also can cover very nicely the constant power flux weakening operating mode. But you need magnetizing currents to maintain the desired magnetic flux. But both of these machines can in fact vary the magnetizing flux. So for example, it will be very easy to reduce the standby losses when you have the flywheel fully charged, spinning at maximum speed, by removing any current from the stator and removing any magnetic flux from the circuit. You could also use a switched reluctance machine, which are also cheap to produce because they have no rotor winding, but the problem with those is that you need to, each stator winding needs to be subject to full magnetization cycle, and whenever you commutate current between the poles, and for that reason losses can be high. Remember, all these electrical machines are requiring a full-scale converter to be connected on the stator of between the stator of the machine and the power system. Okay, there is a different type of configuration which requires a special type of induction machine called a wound rotor induction machine that can connect between a power system and a mechanical system while using a much smaller rating power converter, which is typically placed between the rotor winding and the power system, with the stator winding being continuously connected to the power system, which means that the stator flux, amplitude, and direction of rotation is typically fixed, but you could achieve a very interesting and convenient operating mode within a minimum and maximum rotational speed with a reasonably small converter rating. The advantage is that most power travels between the mechanical system and the electrical system via the stator. For that reason, it's a single stage of conversion with relatively high efficiency. The power installed in the converter, as I said, it's reasonably small. Efficiency, especially at high speeds, would be quite high. The problem is because you have the direct connection of the stator to the power grid, the rotational speed of the magnetic flux is limited by the frequency of the power grid, which in case of a 50 Hertz power system and a single pair of pole implementation of the machine gives you a synchronous frequency or a synchronous speed of the magnetic flux of 3000 RPM. Obviously, you can operate above that, and with a reasonable, let's say, 0.33 maximum slip, you could reach a mechanical speed of 4000 RPM. So 2000 to 4000 RPM would be a reasonable speed range. When using aerospace, which has a significantly higher stator frequency, you could actually get rotational speeds which are typically used in systems that require composite rotors and a significantly higher power density. So the topic of this paper is to analyze the converter requirements to make sure that the converter, which is the most expensive part in this system, can cost as little as possible and therefore making this particular implementation cheapest. Okay, in terms of converter ratings, two aspects are here important, is the voltage rating and the current rating. And in this particular case, you see we have the induction machine connected directly with the stator to the power grid, which has a constant voltage and constant frequency. The rotor windings is connected also to the power grid via a rotor side converter, rectification to a constant DC bus voltage, then inversion to constant voltage, constant frequency of the grid, and in most applications which are high power, you may want to have transformers to connect, let's say, a medium voltage grid to a low voltage converter. And the reason why you want to do that is that typically low voltage, here by low voltage I mean converters rated at less than 1000 volt, so let's say a 690 volt converter would be significantly cheaper per kilowatt installed than a medium voltage converter. And now if you look at the topology here, you end up with two transformers. You have the stator to rotor coupling of the windings, which is subject to a transformer ratio, stator to rotor. Typically, that gives you the ratio between stator voltage and the so-called open circuit rotor locked voltage, typically labeled in the datasheet with V20, which happens when you lock the rotor and therefore the slip is fixed to 1. Obviously, when we operate our system, we'll operate with slips significantly smaller than 1, and for that reason, the available rotor voltage that is seen by the converter will be a small proportion of this open circuit rotor voltage. But it always makes sense that at the highest slip, the induced voltage in the rotor matches the secondary voltage of our adapting transformer that connects the line side converter to the grid. And for that reason, then you can always maximize the utilization of the switches. And also you could then choose, let's say, the most convenient in terms of cost converter that could match to a particular AC voltage levels, because you have control of both the secondary, the rotor number of turns and the secondary number of turns from these adapting transformers. In low voltage applications where you can connect the line side converter directly to the grid, what you want is then at maximum slip the rotor voltage to match the amplitude of the grid voltage. Now we want to also look at what the impact of changing the operating speed would be on the various stresses. We again look at an application where the energy storage system does a constant power cycle. So what we want to have is the product between torque and speed to be constant. Obviously you have one extreme at maximum speed, which gives you a relatively small amount of torque, but the worst operating point will be at minimum speed. We look at the dependencies between rotor power, stator power, and the mechanical power as function of the slip. We can realize that the voltage, induced voltage in the rotor, is inverse proportional with the slip. We can also identify what is the speed range, which can tell us later on what it can be the energy extraction from the flywheel. And then if we assume a 10 kilowatt energy storage system, so 10 kilowatt constant power, with a sleep range from 67% of the synchronous speed to 1.33 of synchronous speed, so a maximum sleep of 0.33. This is what we typically get. A relatively symmetrical behavior of the rotor induced to voltage with sleep, which gets equal to 0 at synchronous. And also a behavior like this where we look at stator power and rotor power as dependent with the slip. And now the big problem is that at minimum speed, when torque is maximum, also the rotor power tend to be much higher than the rotor power at minimum speed, mostly because the rotor current is significantly higher at minimum speed because of the torque requirements. Okay, so again, to summarize, the rotor current seen in a diffig would be proportional with the ratio between maximum and minimum slip. which results actually in a linear behavior here. So the lower we want to operate our flywheel to maximize the energy extraction, the more current rating we need to have in the system. So it costs more in order to operate towards lower speeds, which is this end range here. And in terms of energy, if you look at this flywheel as a bucket, the more you want to go to the bottom of the bucket, which is this area, the more expensive it is to operate, because instead of working on a linear behavior of energy extraction versus slip, you start losing more and more. In order to identify these operating points, we built a simulation model where we had the double-fed induction machine operating in constant power mode, 10 kilowatt, between 2,000 RPMs to 4,000 RPMs, with an average, which is the synchronous speed of 3,000 RPMs. And we were able to look at the extreme operating points, so maximum speed means also maximum induced voltage in the rotor, but the power processed by the converter is relatively small because the torque is relatively small and the rotor currents are relatively small, and the worst operating point seems to be at minimum speed, where the torque is maximum, resulting in maximum rotor currents and also a 6,000 watt power processed by the rotor converter. Remember, the rating, the constant power rating of the flywheel energy storage system was 10 kilowatt. So we can also identify here the maximum voltage and currents and the power processed by this converter. We also run some simulations to determine the semiconductor losses separately in the rotor side converter and the grid side converter. Now the grid side converter losses are dependent with the power flow, while the rotor side converter losses are dependent with the rotor current, which is, has the highest amplitude at minimum speed. In total, we end up with an average over a cycle loss of about 73 watt. And also we wanted to compare this situation against the squirrel cage induction machine running between 3,000 RPM and 6,000 RPM. And the reason why we changed slightly the speed range here was that we assumed the induction machine is rated at 50 Hertz, where you actually have a rated voltage supplied to the stator winding, and then you are doubling the speed to obtain the same energy extraction as we did with the double-fed induction machine. Okay, so the stator frequency goes between 50 Hertz and 100 Hertz. It's clear that you get operation mostly in field weakening mode. The active current stays more or less constant, while the reactive current varies in a similar way to the variation of the flux, and we get the 10 kilowatt plus minus charge discharge. And in total, we ended up with about 270 watt average losses in the converter facing the machine and the one in the grid, which is about 3.7 times the losses in the DFIM. But the important part is that these losses seem far flatter than the ones with the double-fed induction machine. And for that reason, you would expect less thermal stress. So in conclusion, we investigated the use of a double-fed induction machine in flywheel energy storage systems. We identified the particularities of the operating points where the real stresses appear, and also where we have the worst in terms of peak currents and losses. We determined some analytical models for deriving these stresses. We also built simulation models to determine the behavior of the system and also the semiconductor losses. And although the power rating in the converter associated with the double-fed induction machine is not as small as we expected, it's still about 40% less than the 10 kilowatt processed. Well, we can also produce 3 times less losses, but the real thing is that indeed we have not looked at overall loss, which will involve losses in the electrical machine, and this may be something that we can keep for future work. Thanks for your attention, and hope you'll have the time to ask some questions.